let's see how Newton's method works out in an example. So let's see if we can find the first positive solution to this equation, e to the x equals 3x, correct to 5 decimal places. Well, remember, Newton's method really only solves here's the formula for it, but remember what Newton's method finds approximate solutions to is an equation that looks like f of x equals 0. And our equation doesn't look like this. So before we can start using Newton's method, we first need to rearrange this equation. Now, no matter what your equation looks like that you're trying to solve, it is always possible to make it look like f of x equals 0. All you need to do is move everything to one side, because then there will be a 0 on the other side. So if we just move this 3x to the other side, we get e to the x minus 3x equals 0. And so the function that we're going to use for Newton's method is e to the x minus 3x. Okay, now to do Newton's method, of course, we're going to need the derivative of f, so let's calculate that now. F prime of x looks like it's e to the x minus 3. Also, we need some idea of where the first positive solution is, right? We've seen that if you, as an initial guess to get Newton's method started, if you start too far away from the x-intercept you're looking for, you might not end up headed towards the x-intercept you're looking for. So we need some idea of where the first positive solution to this equation is. Well, if you look at x equals, now this does involve a little bit of guesswork, so I'm going to be pulling some x values kind of out of thin air. If we just look at x equals 0, on the left-hand side of this we get 1, and on the right-hand side we get 0. So when x is 0, the left-hand side is bigger than the right-hand side. When x is 1, then we get e to the 1, so that's e, and on the right we get 3 times 1, that's 3. So at x equals 1, at x equals 1, actually the right-hand side is the bigger one. So somewhere in between 0 and 1, these two are switching which is bigger, but that means somewhere in between 0 and 1, they're actually equal to each other. So there must be a solution, because this is continuous, because both of these functions are continuous, there must be a solution between 0 and 1. So why don't we start out with, for our initial x value, why don't we start out with a half? We know there's a solution somewhere between 0 and 1, so a half seems like a decent place to start. Okay, so now we have a function for which we are looking for an x-intercept. We have the derivative of that function, and we have an initial guess for our x-intercept, and this is enough to get us started with Newton's method. So our next approximate solution, x sub 1, is going to be the x value from the step before, which is x sub 0 minus f of x sub 0 over f prime of x sub 0. Right? So this is going to be 1/2 minus f of 1/2, which is e to the 1/2 minus 3 times 1/2 over f prime of 1/2, which is e to the 1/2 minus 3. Now, typically in Newton's method situations, to calculate this new approximate solution, you're going to have to just get a decimal approximation. Typically, you won't be able to get exact values, but calculators produce enough decimal places that the approximations we get from using this formula, just the sort of error introduced by using decimal approximations in this expression, are going to be usually much smaller than the error that we're going to allow anyway, so it should be fine. Now, because of the quotient in this formula, you do need to be very careful when you're entering this into a calculator. It's very easy to accidentally let part of this denominator escape from the denominator if you don't use enough parentheses when you're entering this into a calculator. So you should probably get in the habit of, as you enter this into a calculator, always put parentheses here and parentheses here, just so that you don't actually accidentally get things escaping from your numerators or denominators. Okay, so with all that said, I'm just going to punch it into a calculator. 0.5 minus, and then parentheses, e to the 0.5 minus 3/2, that's 1.5. Oh, and I've already made a mistake. Okay. You got to watch what you're entering into your calculator as you enter it, because it's very easy to make a mistake. Okay, so 0.5 minus e to the 0.5 minus 1.5. Okay, close my numerator, divided by, now for my denominator, e to the 0.5 minus 3. Close paren, equals. Okay, I get 0.61005965. Since we're looking for a value that's correct to 5 decimal places, we're going to have to keep more than 5 decimal places, right? At least probably 6 or 7. And I've got, what, 8 here, so that should do. So what we're going to do is just repeat this calculation, just repeat Newton's method, until these first 5 decimal places stop changing. Right, so we started out with 0.5, so our first decimal place changed to 0.6, so we aren't done yet, right? We need to keep going. So for x sub 2, we take our previous x value, x sub 1, and put it into this formula. So I'm not going to write out all of these decimal places, but when I enter this into my calculator, I will use all of these decimal places. So 0.61, etc., minus, and now we have to use the formulas for our functions, so e to the 0.61, etc., minus 3 times 0.61, etc., all over e to the 0.61, etc., minus 3. Okay, now dump this into a calculator. If you're doing Newton's method, right, you will, at each stage, you will need to use this x value that we just produced in several places in the next step of Newton's method. So it is a good labor-saving device to save this in your calculator's memory. Usually there's some sort of MR button, or maybe it's MS for store, or what exactly the button is called depends on your calculator, but figure out how your memory function works in your calculator, because it's a pain to have to type in these large decimal these long decimal approximations at every stage. So before I forget, let me store, oh no, that's me. I have to figure out how the memory function works on this calculator. Did I get it? Let me check. Yes, okay, I've got it. All right, so now I can do this formula without actually having to type in all of those decimal values. So I need my oh, I just clobbered it. Okay, so let me get this decimal value again, store here. Okay, now I'm ready. So I need to recall this memory value minus, open paren, e to that memory value minus 3 times that memory value, close my numerator, divided by, now open my denominator, e to the that memory value minus 3. Okay, and this time I get 0.61899677. Okay, so you can see that going from x1 to x2, it looks like the first 2 decimal places have already stopped changing. So just after 2 steps, we have 2 decimal places correct already. So hopefully we won't have to do too many more steps, right? So while I have this value, let me store it in my calculator so that I can make it easy to use for the next step. So for my next step, I'm going to use x2, which I have stored in my calculator, minus e to the x2 minus 3 times x2 over e to the x2 minus 3. Okay, now the fun part of entering this into a calculator. So my previous x value minus, open paren, e to the previous value minus 3 times the previous value, close my numerator, divided by e to the previous value minus 3, close my denominator, and we get 0.619061228. Okay, so it looks like still we just have these first two correct, but the third decimal place didn't change much, so probably we're getting close to getting the third decimal place correct. So let's do this all one more time. So store this x sub 3 while I have it, and then x sub 3 minus e to the x sub 3 minus 3 times x sub 3 divided by e to the x sub 3 minus 3. This time I got 0.6190, nope, yes, 906128. So looks like, let's see, we got this 9 settled down, this 0 settled down, and it looks like actually we got this 6 and the 1 as well. And actually 2, 8, look, all of those are the same. So at this point, we have enough decimal values that have settled down that we can stop. We have at least 5 decimal places correct. What you'll find is that Newton's method, after just 1 or 2 steps, Newton's method starts to rapidly get more and more decimal places correct, right? We started with no decimal places correct. After 1 step, we had 2 decimal places, and then, so still 2, and then 5. And then actually all of them that I wrote down, so 8. So it went from 0 to 1 to 2 to 8, or 0 to 2 to 2 to 8. So Newton's method rapidly, once it starts zeroing in on a solution, Newton's method rapidly gets very accurate, which is really why it's so great.